Hello everybody, welcome to the nap time session at the 55th Design Automation Conference. This isn't quite as bad as doing the one just before the cocktail hour or doing the one just before lunch. So thank you for taking time out of your busy day to come hear our panel, How Close to Threshold Voltage Design We Can Go Without Getting Our Fingers Burnt. I'm Brian Fuller, I'm Editor-in-Chief at ARM, which means I do a lot of writing and content creation for the marketing team, but I've also covered the industry for a long time, mostly at EE Times some years ago. And if you're familiar with ARM, you know that it started about 26 years ago with a new low-power version of RISC at the time, architecture and IP, that was going to do pretty nicely in the mobile space. Low power and compute efficiency have always been ARM's mantra, but how they got there was almost by accident. The goal for the ARM processor back then was to go into Acorn Computer's desktop product. It was very cost sensitive. So how were they going to meet the cost? They had to get it into a plastic package. They could have done ceramic, but it would have been much more expensive. Well, the plastic package had a power limit of about a watt, and if you went above a watt, you had to go to ceramic. Now, the tools available at the time didn't really give the kind of accuracy of power prediction that we now take for granted in today's tools. So the way they made sure they came in under a watt was to use the tools very conservatively. ARM co-founder Steve Ferber called these Victorian engineering margins, on the power consumption of the chip. So in being very careful to make sure it came in under a watt, ARM actually produced a design which came in under a 1/10 of a watt. The power test tools they were using were unreliable and approximate, but they were good enough to ensure this rule of thumb power approach. When the first test chips came back from the lab on April 26, 1985, Ferber and his colleagues plugged one into a development board, and they were happy to see that it was working perfectly. But there was a problem. The reading on the multimeter connected in series with the power supply. The needle was at 0. The processor seemed to be consuming no power at all. The development board they plugged the chip into had a fault. There was no current being sent down from the power supply line at all. The processor was actually running on leakage from the logic circuits. So the low power awesomeness that the ARM architecture is most valued for today was almost an accident. So we're going to go from a watt and a 1/10 of a watt way down to what these gentlemen and their partners are working on today as we shrink and get more efficient in our semiconductor design. So I'm going to introduce from, let's see, your left to your right, our panelists. They're going to give you a state of their world for about 2 minutes, then we're going to launch into Q&A. I have a couple of questions, but then we have microphones here, so don't be shy, because the audience tends to ask some of the more probing questions in these panels. So first up, to my left, is Scott Hansen. He is CTO and founder of Ambic Micro. He's an expert in ultra-low energy and variation-tolerant circuits. He championed the development of Ambic Micro's SPOT platform at the University of Michigan, along with his fellow co-founders. Next up is Lauri Kaskinen. He is CTO of Minima Design Processor, which he co-founded in 2016. His expertise ranges from ultra-low power to design to high-level realization of systems. Lauri is an adjunct professor at the University of Turku and previously spent a year of his postdoctoral study on a Fulbright grant at the UC Berkeley Wireless Research Center. Next up is Dr. Mahbub Rashed. He is head design technology co-optimization for Global Foundries, where he's responsible for technology and architecture of advanced FDSOI and FinFET technologies. He has more than 40 US patents and has authored or co-authored more than 30 papers. And last but certainly not least, Paul Wells is CEO of SureCore. He's worked in the semiconductor industry for more than 30 years, and in 2011 he co-founded the company. Prior to that, he held various management roles at Pace Networks, Genic, and Fujitsu Microelectronics. Welcome, gentlemen. So, Scott, You get to lead us off,
Yeah,
so
yeah.
inspire us with your challenges and solutions, your view of
So
the world.
I want to start by saying that I think it's inarguable that energy is more important now than it's ever been before. Okay, whether you're a designer of a server chip or you're designing wearable devices or hearing aids or whatever, power is at the top of your list of concerns. And so by extension, that means that near threshold and sub-threshold design should be great tools available to you. It's a great time to be getting into near threshold and sub-threshold design. I'm certainly a fan. At Ambic, we design sub-threshold chips. We use it for power management, for cores, for memories, for all sorts of things. But I also want to pitch a few words of caution. As much of a fan as I am of sub-threshold, we have to be cautious. There's always a tendency when there's a new architecture, a new technology, to start throwing out new architectures and new crazy ways of doing design. Here's something that's very important. Our customers probably spend weeks designing hardware, but they spend months designing software, and so you have to give them a solution that's usable. That tends to point towards standard synchronous design. It points towards companies like ARM, Tensilica, Siva that have huge ecosystems of software. So there's a tendency to want to break away from that, and my strong advice is don't do that. So the next thing is that I think there's also a belief that magic transistors are going to save the day. So we'll hear about FDSOI. I'm a big fan of FDSOI. I'm a big fan of FinFETs, but they don't magically make sub-threshold and near-threshold design easy. They make it easier. It's one chip that we can take away from that giant block, but it has to be accompanied by good architectural design, good clock tree design, good power management design, good power domain design. So don't look to that to be the one magic bullet that solves everything. At the same time, having a standard cell library that's suddenly magically characterized at low voltage is nice, but it's not the solution to everything. And we spend, just again to put this into context, we spend a few man-months characterizing libraries and getting our standard cell libraries ready for design, but then we spend man-years developing our products. So just be careful in assuming that there's any magic solution to making sub-threshold and near-threshold easy. And so I'll back up and say, again, I'm an optimist. I believe in sub-threshold and near-threshold. I think that it takes a team of people like the panelists you see up here to make it all happen. We've chosen to collaborate with TSMC and with a variety of IP vendors. I expect that these guys will have similar stories. So if you're considering it, you can't escape design fundamentals and having a good architecture, and make sure that you've got a good team of partners around you to make it happen.
Lowry, any magic solutions in your world?
Unfortunately, no. No, I'd love to. But hey, how does near threshold, sub threshold? What's the good thing? So I don't think that was mentioned yet. So it's all about VDD, yeah, DRT. So you take VDD down and you get energy power benefits to voltage squared. But what's the bad thing that happens? Well, I mean, Scott talked about it. It's variance. You really don't know how fast those transistors will be. So what we do at Minima is we bring adaptivity to the picture. And exactly like Scott said, you still have to be completely compatible with all of the stuff that is already out there. So with the software, with the hardware. But we believe that we've brought a small adaptivity into the picture so that the system can really define its own operating point. And if you're looking at near threshold only, it can define that point, within a small voltage range. But then what we bring to the table is also an ultra-wide DVFS, where you can get then almost all of the performance back that you would at nominal, which you lose at near threshold. And how we do this is a really vertical solution. So some of the stuff is very similar to Ambic, like characterizing the libraries and looking at that. But then we bring some hardware IP there. We also bring some software IP, and it's a really vertical solution with a number of nested feedbacks. And very important to that, exactly like Scott said, is that we also have very good adaptivity to the use case. So we can take the CVAs exactly, we can take the ARMs, and so the starting point is exactly the same, and I think that's pretty much it. Short.
Short and sweet.
Yes.
Thank you.
Yeah.
Mahbub.
Okay. Yeah, so since my team is responsible for the architecture both in FDSOI and FinFET, so I have the privilege to kind of at least experience the both pros and cons of the both technologies. And so when we develop the 22 FDSOI or 12 FDSOI and 12 LPN7 versus the FDSOI technology offers a better control, because it has two basically front and back gate. But at the end of the day, the real challenge is that a lot of the low power techniques that we have been traditionally used in the last 10, 20 years are basically mean W, single fin, if we can do that, longer L gates, higher VT to minimize the leakage power and basically dynamic power and control the non-critical path. Those things can start to kind of orthogonal to low VDD. So as you go down to VDD close to subthreshold, your choices of transistors are very limited, maybe one transistor. And how do you design with the one transistor? And the same thing, like you cannot go down to smaller L gate, W, because of the challenges that lead to a more variation. So the tricky part that I learned throughout the work is that how to optimize and do like a lot of the experiments, both from a design side and a silicon learning, and how good the model is compared to the silicon at those very, very close near threshold voltage, and how you characterize the silicon to model and understand and really optimize the real trade-off between the traditional, we call like a low power techniques versus the ultra low VDD near threshold. And FDSOI has inherently some benefit compared to FinFET, and if we can really use that with the adaptive body bias, then we may solve some of the critical challenges that we see today, and that can be solved.
Thank you so much. Paul, last but
Thank
not
you.
least.
Thanks, Brian. So, as the panelists have alluded to, the drive for cutting power in medical IoT wearables is absolutely relentless. Consumers are expecting more and greater levels of performance and functionality than ever before. And what dynamic micro, what Laurie's talked about, sub-threshold, near-threshold designs, these are some of the techniques that developers are using to cut power consumption. The one challenge with these techniques is memory, SRAM. SRAM is really the missing link in helping you get to these ultra-low voltage designs. SureCore has addressed this challenge by developing a single supply rail memory that can scale with the logic all the way down to the bit cell retention voltage. That means that when you're down at these very low voltages, where of course nobody expects you're going to get fantastic levels of performance, but certainly enough to do such things as speech recognition, you can have the memory working in tandem with the processor. And then when you really need to do something more serious in terms of computing, you can ramp the operating voltage of both the logic and the memory, scale up to the nominal voltage, and then start operating in the tens and hundreds of megahertz and do some really useful computing. We've got our patented Smart Assist circuitry, which allows this to happen, and it's completely process agnostic. We've tried it both in bulk processes, FDSOI processes, as well as FinFET processes. So this, we believe, is really we're addressing the key missing link in achieving these ultra-low voltage operating systems.
All right, thanks, gang. So let's start broadly and dive down as we go through the questions, and I'll throw it open in a couple of minutes to the audience. You've touched a little bit on aspects to these questions, but what do you guys see as the challenges, number one, in design, the big challenges in design, and number two, in test? Who wants to go first?
Well, I guess I'll start. So, okay, we alluded to the process variation being a big thing. When you become exponentially or nearly exponentially sensitive to process variation, temperature, and voltage, it creates a whole host of design problems, whether it's designing your memories correctly or just achieving time enclosure on normal digital logic. It can be very challenging. Designing a clock tree is incredibly challenging. I mean, what is not challenging is probably a shorter list than what is challenging. Okay, so everything is extremely challenging. Being adaptive, as Laurie said, is the solution. Okay, that's it. And the question is, how are you adaptive? And all of us probably feel that we have some unique secret sauce there. Test is something that's really interesting that probably, I guess I have a unique insight on having, we actually build chips and sell many millions of chips. And there's been a pretty tough learning curve there, right? From ensuring that your test time doesn't explode. So there's a lot of sensitivities that we have, there's a lot of potential failure mechanisms, and you have to be careful that when you actually bring these chips out that you don't have incredibly long test times or yield numbers that are very low. And so it's great to be adaptive, but you have to have an adaptive approach that doesn't cause test time to explode. And so I won't go into specifics there because obviously that's some of the secret sauce that Ambic has, but that's a big challenge, and it's one that we've had to solve and work very hard at solving, and it's something that we continue to get better at with each generation. The bottom line is this: testers are not designed for subthreshold circuits. They're not designed to measure the kinds of tiny currents that we use, and we use subthreshold both on the analog side and the digital side, so you can imagine if you have tail currents on the order of 10 picoamps for your typical analog circuit, it's very challenging to tune that on the test floor. Okay, so it's just a very noisy environment on the test floor, and it's something that you have to look to manage. And again, you have to do so not just to make chips work, but to make them work at a cost-effective price point.
Anybody else want to weigh in?
Yeah, I could add to that it kind of ties into the design time. So if you're designing for bigger voltage ranges, if you just use the conventional way of designing, then you're signing off at a huge number of points. You can easily get hundreds of corners where you have to sign off. So and I guess probably we were body bias over there and some adaptivity over here, maybe some more here. That just is the first showstopper if you want to sign off in a conventional way. And then when you start to understand that where can you shorten that process when you start to understand what you're exactly doing, and then that ties into the test also. So if you're not going to be in that corner ever, then you don't really have to test that and with the speeds and everything, and goes into startup algorithms, and exactly like Scott says, that's a lot of where the secret sauce will be. And
yeah, I think the main challenge for both for the design and test is that from a design side, you really need to make sure that you do most advanced kind of like a characterization setup like LVF methodology, not like a AOCV or because the more accuracy that your library and cell characterization can provide, the better you are, right? At the same time, the model to silicon correlation, not from like a simple inverter NAND NOR, but pretty much you need to look at all the cell lists that have in the library and really look at like all the way to low voltage and see how close they are, compared to silicon, and make sure that you eliminate those cells that are really flaky or high stack, So really need to go deeper level to really eliminate any risky element in the flop or a stack gates, and then of course characterize with a right, kind of like a accuracy, and then of course in a design you really make sure that you appropriately depend on the size of the block, if a large block and how much hole margin you want to take it for the scan path versus, and then of course the clock tree and other design. And in a test side, you need to make sure that a lot of these tests we do like for customer, you need to make sure that the spec of the product is being tested properly, right? Because that is the key. At this ultra low voltage, you don't want to have like a product. If you have really product like -40 to 125, then you're out of luck because your VT is going to go to the roof between these two and hole margining, and you need to take so much margining. So you need to understand the product spec and test it accordingly with that reduced spec or whatever it can be to provide exactly more like a targeted application-based design.
From the perspective of SRAM design, of course, you have the usual full suite of statistical analyses you have to implement, but we've had to go one step further to cover the extremely wide operating voltage range, and that includes putting in place some key parametric benchmarks, analyzing the design, understanding exactly where we're going to have some key challenges in the design, measuring slew rates. In fact, we have a parametric suite that allows us to analyze every node in the design across all process corners and ensure that the key metrics for each of those nodes is met. And in that way, we can ensure that we have a very robust and very stable design.
So, Paul, because we ended with you, we're going to resume with you on this question, but the rest of you guys feel free to jump in. What's the difference about low voltage design for memory versus digital, number one? And where are we with low voltage analog design?
Well, I mean, effectively the periphery of the memory is effectively low voltage analog, and as I said before, we have to be very careful that we are addressing the key parametric issues. What you often see across process corners is pulse flattening, and pulses can very quickly disappear at these low voltages. Taking into account the variance of the process variability, which is greatly exacerbated at the low voltage, is key as well. In terms of digital design, then I think I'll probably defer to these guys here to comment on that.
Well, yeah, you're exactly correct. I mean, we'll probably hit the 3 sigma points, but you'll hit the 6 sigma points. So
That's what we aim for.
Yeah. But maybe we should take the analog.
Yeah, I can speak on analog. So we do, I said earlier, we do subthreshold and near threshold, well, subthreshold analog. We do a mix of low voltage analog and high voltage but subthreshold analog, right? So imagine I've got an amplifier, I apply 1.8 volts to it, but I dial back the tail currents to picoamps. So, you know, the VGS across any given, or on any given transistor is subthreshold, but on the whole, you've got a lot of headroom to work with. That's generally our preferred region of operation. It suffers from all the same problems that you get in subthreshold. So there's process sensitivities, there's facts that the models don't match, and there's all sorts of other challenges. And actually, one of the major challenges is every circuit topology that we learned about in textbooks doesn't work. It's all based on saturated transistors or bipolar transistors, and suddenly we have to use a subthreshold device, which is very different. So a lot of the topologies we learned don't work. So band gap reference, for example, we had to completely reinvent all of that. With all that said, it's possible. It's something we do today. We are proving that you can be very robust. This is also an opportunity for me to maybe throw another cautionary word out there that subthreshold is not the one-size-fits-all tool for everything. If you want to build a 14-bit 1 megasample per second or 10 megasample per second ADC, probably subthreshold is not your best tool. Maybe it's a tool that can be used in some of the surrounding circuitry, but it's not your best tool. You have to be more than a subthreshold expert. You have to be, as we like to call it in AMBIC, we like to talk about picojoule fanatics, right? You have to think about energy all the time, and from your architecture to the way you do your clock design to how you apply subthreshold. All of those things have to be coming from a picojoule fanatic mindset. And in analog, sometimes the subthreshold relevant, sometimes it's not.
I want to thank you, by the way, for remembering one of our conference call recommendations to wear funky socks.
Yes.
You're the best.
Yeah, thank you. Thanks for noticing.
Let's talk a little bit about manufacturing, and I'm looking at you, Mahbub, because I think a lot of people look to the foundry world to solve all their problems.
Yeah. Unfortunately.
Right? So talk a little bit about FTSOI, FinFET, the various benefits there.
Yeah, so I think the key strength for FDSOI is basically ultra low power, right? Because it really gets you the benefit of the fully depleted with the 2-gate control. As you can see that, you know, we are the only one right now with the 20 FDSOI getting like 0.4 volt for a lot of customer, you know, library and PBT working, you know, in production mode. And 0.4 volt, we have only one transistor basically that works, and of course it has a 5 L gates, and but it's very close to the VT. But because of the body bias techniques, you know, we can basically manage it and provide the full guarantee of the yield. But so if we really want to look for like a really ultra low power close to the subthreshold regime operation, then FDSOI definitely has a significant advantage because of the dual control of the top gate and bottom gate, because roughly you have around like for every 1 volt, you get like 80 millivolt of VT change. So you have a lot of control because you can control the VT by 80 millivolt. And the way you manage the leakage is basically, we manage the leakage that we do 2 options because we have these 5 L gates, and we also have a dual trimming where you can basically for distribution with a faster silicon, you can have a 0.4 volt without having the subthreshold of the well kicks in, and you can bring those distribution back to close to typical and reduce leakage by 3x. So you can have a very, very tight distribution and not paying the penalty in the leakage where you don't have a slow part. And the further away from the VT, you have a control on the design not to add a lot of margin. On the other hand, I think FinFET definitely has a application where I think roughly like 0.5 volt. So I see between these 2 technologies, FDSOI can operate today at 0.4 volt pretty reliably with the help of body biasing. FinFET, because of that, at least the traditional techniques, design techniques, it's like 0.5 volts. So you see that roughly around 80 to 100 millivolt gap, and if you're really very small design, not a lot of back-end loading, and then medium to small design, FDSOI is a way better than. But if you really go a lot of back-end loading, and you need a lot of drive, of course, FinFET with a 3-dimensional transistor kind of kicks in, and then you can stay at a little bit higher voltage, and still you can manage the power with a. But I think the biggest challenge right now, which we are trying to solve in FinFET, is like how to get to a single fin. As you know, that both Global Foundries 14 and other foundries, the minimum fin is 2 fin, and really get to a low voltage, you need to really first get 1 fin. And to get to 1 fin, your variability increases, and that also contradicts to your lowering the VDD. So I think the trade-off that needs to be solved, to really get to the bottom of it.
How about some of you other gentlemen from your perches at a different spot in the ecosystem? Are you, do you have a feeling one way or the other about what's a better approach? FDSOI, FinFET?
FDSOI versus FinFET, I think both offer steep subthreshold slope, both offer reduced AVT, parameters of random double fluctuation goes down. That's very attractive to me. Certainly the backgate control is very interesting. I think both are probably of interest. Both are a little bit scary from a cost standpoint, right? There's just sometimes where you cannot economically justify going to advanced nodes. I think a lot of the industry tends to think that everybody is building 10, 7, going to 5 nanometer chips, but the truth is that a huge number of customers are still, or companies are still back building 40 nanometer, 65 nanometer, 90 nanometer and above, and unfortunately those just aren't tools that are available to us there, and economics just dictate that. So that's my statement. FDSOI, FinFET, both wonderful, but I don't think it's realistic for the vast majority of subthreshold and near threshold use cases today. It's probably actually not even a realistic option. FDSOI is probably the next realistic option because it's a bit cheaper.
Lowry?
I love FDSOI because it gives me one more knob to play with. Okay, that might sound scary, but it actually does fit very well into when you know what you're doing, and it does fit very well into the DVFS loop. So what you essentially do is use the BB to reduce the variance, and then use the AVS to minimize the energy. And while it might seem that you're twiddling many knobs at the same time, it's actually very doable to do both. And I'm a fan. And this is not a knock against FinFET. FinFET is, I mean, also you get very fast chips there, but being a big fan of adaptive stuff, BB is good.
We proved a lot of our power saving techniques on FDSOI to start with, so we definitely see the advantages of FDSOI. And I think in terms of, as Scott was saying, where the industry goes is ultimately not dictated by the process anymore, it's by the economics. But I think FDSOI is very rapidly starting to establish itself as a very cost-effective means for some of these newly emerging markets.
So I want to dive into that from something Scott said. So is this a technology that is going to be confined to larger leading edge design companies? And
Is sub-threshold in particular?
yeah. I mean, in other words, economics rules the day. So these are companies that can absorb those sorts of costs, or at least can take the risk to do that kind of design.
Yeah, so it's certainly easier to push voltage lower today if you're at a leading node that's using FDSOI or FinFET. So yeah, in that sense, that's true. Of course, there's still a demand for low power in the older nodes, right? So we sell products today at 40 nanometers, 90 nanometers, and 180 nanometers, and each of those nodes is economically justified, and in all of those cases, I probably cannot justify going one node lower for that particular product, cost-wise. And so subthreshold is still important there. It's still a tool that I have to deploy. So as long as energy is important to those markets, and it is, then I think it will get deployed, but there's a bit of a higher barrier to entry. So that's probably a fair statement. It will get used more readily in the more advanced nodes, and then maybe trickle backwards into the older nodes.
Lowry?
Yeah, I think it's you have to look at a Pareto point like many times. So at least two variables, and I think that the other variable here is the use case and how much performance, aka how much horsepower you need there. So you'll have still for a long time you'll have use cases where you really just want to minimize the absolute energy, but you don't need at any point a lot of performance. You know, think about something like monitoring concrete or you know, the collapsing bridges, things like that. So it has to stay there for maybe 20 years and it has to work, but it's not doing much. It's reading a sensor maybe every once an hour or something like that. And water metering, things like that go into there. And then some simple radio system on top of that. But then again, another use case is what you're seeing a lot of here is voice wake up. Okay, that's always on, so it will be listening to you all the time. But it is actually doing somewhat of a complex operation, and it will need a lot more horsepower than the concrete meter, and somewhere around 10 megahertz. And if you want to do then AI on top of that, then you'll need a lot more than that 10 megahertz. So definitely, I think everything is needed. Exactly as Scott said, up to 180, because you really have to look at the use case and the application where it's going.
So I want to throw it open to the audience. You're all experts in this area and probably have some really good, compelling questions. If you could identify yourself before you ask the question, that would be awesome.
Hi, Pavilion from Synopsys. I have a question. All of you guys mentioned large variability, controlling variability, and so on. Can you also define what is large compared to mean? When is it that you call it something large?
When do you call something large? I mean, we easily see variability, delay variability. 1 sigma could be 100% of the delay of the gate or more. I'm just throwing a number out there.
Yeah.
I'm sure you guys.
I mean, before I put that to Paul, I mean, you have to think of the circuits. So I'm the logic guy, so I have the easiest because the paths will be long, and then there will be averaging out. But then when you go into SRAM and Paul, then you'll have maybe 10 transistors on the whole path, and if one of them is really bad, then you'll immediately see it in total performance. So that's why I mentioned that 3 sigma versus 6 sigma. Those guys see the worst.
Yeah, I mean that's partly why, as well as doing the statistical analysis, we introduced this parametric analysis as well. But in terms of the differential between operating at V nom versus down at say 0.6 volts, then you can look at say 30-40x in terms of the difference.
Yeah. So generally we use like a kind of rule of thumb. Like for a large design, we use like a 10% because if you have to have a whole time fixes for the scan path of 6 sigma, if it's more than 10%, it's going like 60% of the variability. Then you have to add so much hole buffering. So I think this is the big challenge of this near threshold design, is that as the variation goes up, your variability of the flop and the circuit goes up, and you have to add extra hole buffering, and that can take away all the area and power benefit that you go by the VDD lowering. So we use 10 to 15% number depending on the block and size, and figure out whether we have to do 3 sigma hole closure or a 4-5 sigma.
Sorry, this 10 to 15% is a 15?
One sigma.
1 sigma, that's compared to mean, you're saying?
Yeah.
And that's, for example, in timing is a path arrival.
That's correct, yeah.
And then one more difficult thing is Gaussian versus non-Gaussian.
That's correct, yeah.
So a lot of almost everything that you have on the market now assumes that everything's Gaussian, but it's actually not. So you also have to, in the corner cases, look at non-Gaussian performance and either do it yourself or find somebody who understands.
Who out there is doing threshold voltage design right now? Because you have a golden opportunity to hold these gentlemen's feet to the fire with your challenges or questions. Nobody? We're so far ahead of the curve, it's not even funny. It's good. Speaking of being ahead of the curve, and any time in our industry when we have sort of a new technology flowering, if you will, right? There's a bell curve in terms of the maturity, but there's also a bell curve when it comes to resources. Okay, you think of the perennial one, which is analog mixed signal, right? It's tough to find those engineers. Is this one of those cases where there's not enough specialization yet in this area?
It's hard. Recruiting is hard, and we're a startup company, or we're a small company. So recruiting is always one of the hardest things to do, and when you're talking about a new technology, that's very hard. What we found is a couple things. Designers who are used to designing in very, very advanced nodes. So let's take digital designers that work at the big processor companies working at 10 nanometers and below. They're used to a lot of the challenges that we face at, say, 40 nanometers. Okay, so they tend to make good designers. They're very performance driven. They have to be reset in how they design things, but they prove very adaptable. The same thing on the analog side, we find that designers who are used to designing really constrained systems, whether they're designing RF or they're designing audio systems, we find that they have the right skill set, which is to say, how do you hyper-optimize for a few key quantities up against major noise constraints or whatever. So we haven't found people who spent 10 years doing subthreshold design. By definition, it's just something people haven't done. But we've found people who are very trainable and can adapt. And that's been key.
That's similar? Mahbub, you're nodding
so
your head.
Basically in my team, as you go down to the VDD, your digital and analog gaps kind of close down, right? Digital become analog. So I try to use my analog designer to design some of these, flop to look at ultra low voltage. So it's kind of like you need to know a lot of transistor level. You need to know basically circuits, silicon data. You need to be paranoid like analog engineers, not like a running tools. So you need to have a lot more experience both in transistor and circuit and SOC flow. It's all combined because it's not like a one thing. It's like you have to really optimize the flow, the characterization, the silicon to spice correlation, as well as the understanding what kind of like a clock tree or a hole buffering techniques. So it is a kind of very, very more intensive work and require a lot of expertise.
Well, one of the challenges we've faced is not only do you need designers with analog mixed signal skills, in order to efficiently build SRAM compilers, they also need software skills as well. So that really kind of makes finding the right people extremely challenging.
Yeah, in Finland, it's probably even more harder than over here. But what the good thing is that at some point a certain communications company was 40% of the GDP. So there are a lot of people who know their communications, and again, there's been a lot of adaptivity, from to getting all the mobiles to work. So that's something that plays in our favor. But it's a small part, and the hiring is very, very hard.
All right, here comes the tough question. Chris?
Okay, I'm just looking at for people who are beginning to investigate this area for their own designs, what sort of power modeling techniques do you recommend to people that would use to actually assess how far down in voltage they go? Because you've got the work that come out of Michigan about this sort of bathtub curve of total power. Leakage dominates once you go below the threshold, and then active at the other end. I mean, are there techniques that work for actually modelling that well, or do you tend to find that the variational problems you get at the very deep, very low end, tend to overrule any considerations about how much energy you think you can sort of squeeze out of it?
Well, one thing I always say to the customers is that with at least with our adaptive stuff, we'll guarantee the performance, but there's no free lunch. So what happens if you guarantee performance and either your transistor models are not good or there is a lot of variance, where that ends up is actually in the power. So what your data sheet, and this is something that you have to realize if you're looking at this, so what your data sheet will look like is that your performance is guaranteed, but then the variance of the power starts to change. And that gets a lot bigger. Again, there's averaging. If you have a bigger system, it averages out even more, but that's something you're not going to escape.
Yeah. So I find that this is very hard. Modeling energy in a system, selecting the voltage is very hard. It's very iterative at our company. So VDD is effectively a design variable until right before we tape out. So it's something that is subject to change throughout. And it starts with a spreadsheet-based process. It's really ridiculous that in 2018 anything in chip design is spreadsheet-based, but it continues to be for us. In large part, energy modeling is spreadsheet-based. We do some kind of Python-based power simulations. We'll then graduate to, so we use, I don't mean to promote certain products, but we use Cadence tools. We use a completely standard flow there, and we use the power analysis functions that are available there. But the truth is that the design flow that's provided by the CAD vendors doesn't really contemplate low voltage, doesn't really contemplate voltage being a design variable constantly. Just actually look at what the foundries generally give you. I see Global is changing that to some extent, but the foundries give you VDD plus or minus 10%. So there's just, you kind of do there, or you snap up one level higher. That doesn't really work here. A big gap that I see is that the CAD tools, as much as they've started to include knobs for power, they're still fundamentally performance driven, okay? It's still fundamentally about time enclosure, which I get because your chip just doesn't work if it doesn't hit, time. If you don't, these are synchronous designs. If you don't run at the right clock frequency, it won't work. So function comes before power. But we find that the power knobs that exist for both on the modeling side as well as on the optimization side are very surface level and need a lot of work. So to you CAD tool guys out there, CAD tool people out there, please fix this.
Here, here.
Oh, you didn't, I thought we're going to have a follow-up.
Oh, there we go. Actually, I do have one. Actually, again, it may be the straight man question for Ambic, in terms of partitioning at sub-threshold, near threshold. I think the RTC on yours is sub-threshold because it's kind of always on, so you have to eat the leakage, as it were. And but for other things, you can actually go higher. But is there a point at which power gating actually simply beats near threshold? You just run fast and switch it off.
That is actually what we do. So it's back to you alluded to at Michigan. There was some work that showed as I reduce VDD, energy drops, and then at some point it kicks back up. And as long as number one, at your target voltage, you can achieve the desired performance, and number two, you haven't gotten so low in voltage that leakage starts to dominate, then you should always run at the lowest voltage that you can. And so we do end up, in most of our cases, we do end up racing to completion. We run at a low voltage, we race to complete, and then shut down. Especially as we go to more advanced nodes, there is a point where you don't want to go any lower because suddenly leakage starts to dominate. You should do that. So I think for most of the workloads that we're chasing, low voltage near threshold is the right place to be. But we do actually have cases where customers need to run at elevated voltage because they need 100 megahertz or 200 megahertz, and we can only provide that by elevating the voltage.
So basically, it is depending also on the application. So like a cryptocurrency applications looks like can run like a maybe up to 50 to 100 millimeter lower, that U curve, then a IoT and then a mobile, because depending on like a percentage of the leakage versus dynamic power. So if the leakage power is much less, you can go choose a much lower VT transistor and can still be total power optimized, versus if the leakage power is more. And also the temperature spec is a big factor on that. And then RTC or something like that, much lower temperature spec, you can run a much lower voltage versus in 85 degrees C or versus like a 125 C. Yeah.
Cheers.
Thanks, Chris. So we're bumping up against time. You'll recall when we started this journey early on that this panel was going to be a half an hour, and we could probably have allotted 90 minutes to do it easily. So thank you for your time. But I want to start with Paul and then come back this way and give you guys a chance to, given what you've heard from the audience, from the questions from your own interactions, just sum your position of the world.
So I think it's going to be the way of the future, certainly for some of these newly emerging markets which demand low power. The EDA industry certainly needs to do something to help general purpose low voltage design. The foundries, as we've heard, global foundries are already addressing this in terms of model accuracy and ensuring that in the sub-threshold space the models are more accurate. From an SRAM perspective, certainly from our architecture perspective, the lowest voltage you can get to is the bit cell retention voltage. If you go beyond that, of course, then you're going to suffer data loss. So some of the new FDSOI technologies are extremely promising in terms of the level of the bit cell retention voltage, which means the memories can be pushed down into genuine near and sub-threshold spaces. So yeah, I think this is just going to gather pace as we move forward.
Yeah, so I think we need a lot of increased collaboration between the foundry, EDA, and then the actual design companies, right? Particularly, a lot of the variability comes from layout constraint and then the transistor mismatch, as well as the modeling. Like LVF is a great thing, and we found out that is doing a LVF modeling versus AOCV, you can lower the V mean by 50 millivolt, and that really helps because now you don't have to add so much margin. So I think the EDA community can help a lot by keep researching and really helping us together build that next generation ultra low power subthreshold design. I think it will happen.
I might touch on the application side. So I believe that this will be very important because there are a number of applications there that which will require what we now call edge computing or fog computing. So pushing that computing, into the sensor device, into whatever is sensing, and the reason why I think this is the wireless bandwidth. So if you have the trillion radios to plug one of the larger companies, you can't do anything meaningful if you're just transmitting everything into the cloud. So that's why you need to push that into the smaller devices, and that's where all of this stuff that you've been hearing today comes in.
Okay, I was going to say something, and then you totally changed what I wanted to say. You gave me a great idea. So I think we actually never really talked about one of the key problems with subthreshold, near threshold is it tends to run much slower, right? So we tend to have to operate. I usually say sub 100 megahertz, but I want to make the point right now that that's changing quickly with the work that Global and some of the other foundries are doing and offering new technology nodes, with the work that the architecture companies are doing and launching new MCUs and DSPs and AI cores. We're going to see a tremendous increase in the performance limits of subthreshold. So I think the opportunity for subthreshold and near threshold is going to grow fantastically in the next few years. I bring that up because Ambic is going to, as well as I'm sure the rest of the companies here, is going to be at the forefront of that. We have products in the market today that will run at 50 megahertz. We have some new ones that we'll announce shortly that run much faster. We have some new ones that we'll announce sometime after that run fantastically faster than that yet. So expect to see, this is a great tool that we can deploy now in a variety of markets. Expect to see the addressable market for subthreshold and near threshold grow substantially in the coming years. So if you want to run at a gigahertz, or you want to do a giga operation per second or 10 giga operations per second, consider subthreshold, okay? And if you want to talk about that, come talk to me. We can debate and talk about cool ideas.
Thank you. And thanks to the audience for your time and attention. I'm sure some of these or all of these gentlemen will, chat with you, be happy to chat with you afterwards. Thanks to Jan Willis, who had the inspiration for this panel and helped me herd the cats on it. Thank you so much. And let's have a round of applause for our awesome panelists.